Welcome physical science class. This is my first video for physical science and we will of course improve them over time. I have a camera set up which, because this is my fourth video that I've recorded, I've had 3 math class videos that have been guinea pigs. This is slightly better than those and things will improve throughout the semester. I welcome your comments, your feedback about how I can make these more useful to you, more beneficial to your studies. And I think that the way I'm going to do these is, and at least for the time being, I will tend to have one video for a module, which will focus on basically just the overview of the concepts. Then another one that will probably go over, any of the experiments that I might do at home that are just kind of easy to do in front of a camera. I know this module there will be some, I'm not sure so much about the, definitely not in module 16, maybe 1 or 2 in module 15. And I'll also go over the, the more mathy or technical examples in that second video per module. So basically, until further notice, I'm thinking first video per module will be big concepts, overview. Second video will be getting into more specifics and still doing a little bit of test review with that. So, we're in module 14 right now. We're going to be discussing waves. You may recall from last class, you probably don't because there was spring break in between and, a worldwide pandemic and various other things. So anyway, we talked about 2 different types of waves. And there are more than 2, by the way. Next module we'll get into a third broad category. But 2 basic types of waves. The first one is called a transverse wave. Now think of a wave as like a disturbance, like a wave is oscillating something. So if you have, for example, if you have water, it's going to be like this transverse wave, and the waves that appear on the surface of the water. And those waves are doing 2 things. They are propagating, meaning they are traveling toward the shore. So the wave actually travels, that is its propagation. For a transverse wave, it's going to be, let's say, this way, but somewhere either this way or that way. But then it's oscillation. In other words, as the wave is traveling through the water, what is it oscillating? What it's oscillating, or what it's moving, is the water itself. And in what direction is it moving the water? Mostly it is moving the water up and down. So we will call that the oscillation. So a wave is a disturbance. It's going to be interacting with matter around it, moving it, traveling through the matter. And so the way it moves the matter is the oscillation, and then the path of the wave is the propagation. What would happen if I took these 2 lines, made an angle? Be a right angle. That's aka perpendicular. So a perpendicular angle. So we define a transverse wave by saying that its oscillation is perpendicular to its propagation. I said in class that it's basically like, think of a transverse wave as, what did I say? Basically someone running around waving their arms like this. So you can be like moving in a certain direction. Your body can be moving this way, but then your arm, or maybe how about this, like think of an elephant with a trunk. So the elephant's trunk is going up and down, but the elephant itself is traveling in a straight path. Trunk going this way, elephant going this way. Transverse wave. Now, on the other hand, the other kind is called a longitudinal wave. And you know what? This longitudinal wave looks very sad. It kind of looks like the very hungry caterpillar after he ate too much on Saturday. So I think I'm going to pause the video and redraw that. All right, so here's a slightly better looking longitudinal wave. So again, we defined a transverse wave as saying its oscillation is perpendicular to its propagation. A longitudinal wave on the other hand, is going to oscillate in the same direction it propagates. So I'm just going to write O for oscillation and P for propagation. And we define a longitudinal wave by saying its oscillation is parallel, not perpendicular, but parallel to its propagation. So the wave in the ocean, the transverse wave, it's actually moving water up and down. The oscillation is how it's moving the matter around it, but it's traveling straight. And in the case of a longitudinal wave, it's going to be traveling in a certain direction and moving matter in that same direction. I don't have one, but imagine that I had a slinky right here. If you have a slinky stretched out and you push on one end of it, what happens? Parts of the slinky will bunch up, and that bunching of the slinky is going to travel all the way through it. And then do it again, and it's going to travel all the way through it. And if you just keep doing this to the slinky, you're going to be creating a sequence of longitudinal waves. So the wave is moving the matter, in this case the coil of the slinky, in a certain direction, and the wave itself is traveling in that same direction. So transverse waves, the oscillation is parallel to the propagation. Now we're going to talk about sort of the anatomy of a wave. I've drawn our two kinds of transverse waves. So the transverse wave is the elephant wave, basically, like the wave is oscillating up and down, walking in a direction. The longitudinal wave is like kind of like a chicken, like it's pushing with its head as it's walking in the same direction that it's pushing with its head. So oscillating and propagating in the same direction. Now, some of the characteristics of a wave, I've written them over here already, and this is in part an experiment. Let me know if you can actually like see these colors other than black. So this right here, this expanse here in red, that's called a wavelength. And this right there, I don't know if you can see it that easily, so I'll make a great big one down here. It's a Greek letter called lambda. Lambda. And that's just a symbol for wave length, specifically. Wavelength, not for waves, for wavelength. Now, what exactly is the wavelength? The wavelength is the distance from crest to crest, or trough to trough on a wave. So a crest is a high point. That says crest right there, in pink if you can read it. And a trough is a low point. Highs and lows, crests and troughs. So if I go from one crest to another one, that's going to be one wavelength. And if I go from one trough to another one, that's going to be one wavelength. And it turns out this wavelength from crest to crest is equal to a trough to trough wavelength. And this crest to crest wavelength is going to be equal to this crest to crest wavelength. And this trough to trough one is equal to this trough to trough one. All wavelengths are the same, which is really convenient. Now, we can also talk about the amplitude of the wave. And the amplitude is going to be, it's going to require us to draw a midpoint in the wave. So if I made a central point of the wave going through, the amplitude is going to be the height of the wave, which we can kind of, like in the diagram of the book, they draw it like this. They indicate amplitude. So it's the height of the wave, and in this diagram in the book, it's measuring it from the midpoint. We are now going to address these characteristics of a wave on a longitudinal wave. And this is a little harder to understand. That's one of the reasons why I'm taking some time to go over it in this lesson. So do you see crests and troughs on the longitudinal wave? No. The longitudinal wave is, and maybe you can tell, I didn't do an excellent job of drawing this, it's going to be divided into groups of compressions and groups of rarefactions. That's R-A-R-E-F-A-C-T-I-O-N-S. So what is it when something is rare? It means that it is spread out. There's not very much of it. Right now, finding somebody like, I don't know, in a public park, they are rare, or something like that. Finding somebody in a movie theater. I saw some kind of a meme that said like, where's Waldo's social distancing edition, and you just have like 5 people sitting in a field. It's really easy to pick out Waldo. Compressions make sense. You compress something, you're pushing it in, you're making it more compact. So we have a group of compressions packed in section of the wave, and a rarefaction, a spread out. It's kind of like playing an accordion. Rarefaction. I color-coded these the same as crest and trough because they're the equivalent. You don't really have a high and low point of this wave, but you do on this one, so you have crests and troughs. But here it's a matter of compression. So you've got compressions and rarefactions, and therefore the distance between them is actually going to be your wavelength. So a wavelength on a longitudinal wave, and this is certainly not drawn accurately on the board. I'm just going to do the lambda. It's from compression to compression, or rarefaction to rarefaction. That's going to be wavelength on the longitudinal wave, either compression to compression or rarefaction to rarefaction. So comparison. Transverse wave, a wavelength is crest to crest or trough to trough, and it's equal distance both ways, just like a normal class. I'm dropping my markers. And in a longitudinal wave, it's going to be from compression to compression or from rarefaction to rarefaction, same both ways, same distance both ways. Now, what about amplitude? He doesn't actually explain the amplitude for longitudinal wave in the book, and for years I was thinking, why didn't he explain that? Because it just seems like I was curious. I was like, well, he compared the qualities of the waves and pretty much every other point, so why not? It actually is pretty tricky. It's a little complicated. So basically, imagine this. Imagine that you have your slinky, which represents a longitudinal wave, and you send a pulse of that slinky through. As you do, and you can YouTube this, I highly recommend it, if you do YouTube, you basically, as the wave is propagating, the oscillation is going to result in compressions and rarefactions. So let's imagine we have one point on the wave, right here. I will emphasize that again with another color, just in case it's not coming through well. But no green shows up yet. I'll watch this later maybe and figure it out. So you send that wave through the slinky. What's going to happen to this point? It's going to go like, and this boing thing is going to go back and forth. So let's imagine that when the wave goes through, this goes all the way over here, stretches all the way this way, maybe to this point, and then it stretches all the way back to this point. So wave goes through, and this part of the slinky, which is absorbing the wave, it's oscillated to go all the way from here and then back to here. So from this point to this point is going to be the equivalent of like, over here, the amplitude is going to be like from a midpoint to the top, or you could actually measure it, the midpoint to the bottom of a transverse wave. That'll also be amplitude. Here, you're creating a horizontal midpoint. Your amplitude is going to be the distance from one side of it to the other. That's not in the book, but I just thought you might like to know because it bothered me when I didn't. Either one of these is going to be your amplitude. So, really, what is amplitude? Amplitude is pretty much just how far from the midpoint of the wave, which is a vertical distance here and a horizontal distance here. And it's not the actual midpoint of the wave itself, mind you. It's the midpoint of like just any one one part of the wave, like any one part of what's being oscillated, is how far it's going to sort of elastically go back and forth. So I mean, I could have drawn this here, I could have drawn it here, it's the same idea. Any one part of the wave is going to go back and forth a certain amount, and the midpoint of that is where you measure the amplitude from. Now, what does the amplitude of a wave actually translate into as far as the wave's natural characteristics? It's going to be the strength of the wave. So imagine a wave of the ocean, great big transverse wave, and the taller that wave crest is from the midpoint where the wave begins, the more mass of water is going to come crashing down on you. In other words, the more force there is, the more strength the wave has. Over here, I haven't said this yet, but now is a great time to introduce this idea. Think water wave. Over here, longitudinal waves are sound waves. And so if you have a sound wave shoots through the room, you even experience this on a physical level in your eardrum. What happens when there's a really powerful bass? You actually feel your eardrum kind of elastically go boing like that. It goes in and out. That's that oscillation that's going from the sound wave. And so if it's a slight sound, there's going to be a slight knock on your eardrum tympanic membrane, and it's just going to go boing like that. It'll go there and back and then settle. But if it's a really loud, like some kind of a bass drum or something, just like a boom, it'll actually have a larger amplitude. That membrane in your ear is going to bounce farther, just like same idea as if you have like a heavy person versus a light person on a trampoline. The heavier person on the trampoline is going to cause it to undergo a significant oscillation with a large amplitude, whereas a light person will not. Same thing happens to your ear when sound interacts with your ear. Pretty much the rest of the module is going to deal with sound waves and longitudinal waves rather than transverse waves. But there is an idea that's really easy to convey with transverse waves, so I'm going to do it right now. This is the idea of frequency. Frequency breaks down to a simple equation, which I can write in a really fancy way that looks very foreign and Greek, actually, kind of, and complicated. It is going to be V over lambda. What does that mean? So that actually means speed. They write V, which is a little deceptive because you think velocity, over wavelength. So imagine you have waves in an ocean. And the wave, let's just make up a number. We'll say this wave is propagating at 30 miles per hour. How many wavelengths are in this wave? Let's stop it from looking too complicated. Let's do that. Well, we have roughly like 2.5 wavelengths, because I can go crest to crest, that's one, crest to crest, that's another, and then that's sort of like a half. So in fact, let's make it even easier on ourselves. Let's say exactly 2 wavelengths. We could also measure it by troughs. So trough to trough, and then this would actually be the equivalent of one more trough to trough. So if this is going, you know what? Let's not make up 30 miles per hour. Let us say, let's just pretend, make our lives really easy, that this entire length of wave is going to propagate past this barrier, and I don't know, maybe what's it interacting with? Let's say it's an ocean wave. Let's say there's like someone in an inner tube. Who can't swim. No, he can swim. He's happy. It's his birthday. There we go. So let's pretend that this entire length of wave will take exactly 1 second to propagate past this guy. And he's going to be oscillating as it does. So what would that mean? We have 2 wavelengths passing every second. So the frequency is going to be 2 wavelengths per second. Why is this not working, Lord? Oh shoot, I thought I paused the video. Okay, I found it. So the speed of sound in a liquid tends to be about 3 times faster than the speed of sound in air. So, you know, roughly like 1,000 times, or sorry, 1,000 meters per second through water as opposed to, you know, a third of that through air. And then it'll go an additional 2 times as fast going through most liquids, or going through most solids as opposed to liquids. So it's like, think about that 1,000 meters per second rough estimate of going through a liquid, and then it would be like 2,000 meters per second. So it's like 330 roughly meters per second to 1,000 meters per second to 2,000 meters per second. Rough ballparks. And going from a gas to a solid is kind of like going 6 times as fast. There's different animals that exploit these characteristics of sound in interesting ways. First of all, you probably know that whales will make songs that travel all through just vast stretches of the ocean because sound travels really well through the medium of water. But one thing you may not know is, you know how circus elephants will stand on 1 leg or 2 legs or 3 legs and you know, sometimes stand on top of objects. They actually have a natural instinct to stand on fewer than 4 legs, and the reason is kind of fascinating. I'm going to draw an elephant's foot. You may have noticed that an elephant's foot just kind of has this weird shape to it. It doesn't seem very well defined, but it's purposeful. It's divinely designed for the use of the elephant. Give it some nails, I don't really care how many. So it turns out that there's fatty substance in between the different spaces of the elephant's foot that are really good for detecting sound waves. The sound waves will travel through them well. And so when an elephant is lost, think about, there was one time where I was on a field when a bunch of horses raced by, and I wasn't expecting it, but the ground shook. Like you could really feel the power of the horses running. Think about a herd of elephants stomping around. That's going to make some deep vibrations in the ground. So if an elephant gets lost, then it might try to hear the rest of the herd with its ears, but that's not going to be very successful compared to if it stands on 3 legs. You know, here's your elephant with no detail. There's a trunk, tusks, eyes, smiley face. That looks like some kind of a scary insect slash like flagellum thing. But anyway, not a good elephant. Oh, there we go. That's a good elephant. Much better. So at any given moment, if something is standing on 4 legs, its weight is kind of divided by 4, and how it's impacting the ground. So the elephant's weight is distributed on 4 different legs. So, but if you take the elephant's weight, I don't know, let's say the elephant weighs 1,000 pounds. So standing on 4 legs, you have 250 pounds of pressure on each foot. But if the elephant stands on 3 legs, then you have 333.3 repeated pounds of pressure on each foot. So let me ask you, if you're pushing down with 250 pounds into the ground, or if you're pushing down with 333 pounds to the ground, which one's going to get you deeper into the ground? It's going to be the 333. So when an elephant stands on 3 legs, it may be because it's lost, and then it will feel its weight, you know, it will feel into the ground with its weight, pushing deeper into the ground. So it gets deeper into the ground and then senses, oddly enough, the vibrations of its herd coming up through the ground, through its feet, and then it'll know which direction to go. Pretty fascinating. Another interesting animal fact that's related to sound, we already discussed frequency. And the frequency of a sound wave determines what, hopefully you remember, the pitch, how high or low it is. you probably knew this, but there are certain sounds that humans can hear, and there are certain sounds that humans can't hear, but animals can. I'm sure you knew there are sounds that humans can hear. So let's just say this is our range of what we can hear. Anything and let's say this end is low frequency, and this is high frequency. So this would be like if you're playing a piano, imagine you play lower and lower and lower and lower and lower, and then you get to the point where, imagine that piano goes on forever. You play a note just like low, 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 and it gets lower and lower and lower and lower until you finally can't hear it anymore. You might feel a rumble, but you don't hear it. Once a sound exits our range of being able to hear it because it's too low, you would call it infrasonic. Infrasonic, I-N-F-R-A-S-O-N-I-C. That's going to be this range in here. And one animal that rather fascinatingly relies on infrasonic sound is a tiger. So let's say you have two tigers. And tigers are very introverted animals. They live a lot of their life alone. Let's put a couple of big boys up there. Guess they need some stripes. So if they don't like each other, and they want to intimidate each other, they will growl at each other, and tigers' voices go very deep. So we hear some of their growling, but they hear a whole infrasonic range of growls that we don't. And those infrasonic growls, it's actually believed, injure the tigers, their opponents. So it's so painful for them to hear those infrasonic sounds, it actually seems to cause physical damage. And so they will fight each other with roars before they actually come to blows. Pretty crazy. And then, of course, if you go to the other side, when a sound becomes too high for us to hear, we call that ultrasonic. And ultrasonic waves are very useful. We can use them for medical scans. That's how you do an ultrasound of a baby. And you can even use them because, remember, frequency is the energy of the wave. So low energy, high energy, and just like a singer can, using a high note, break a wine glass, if you hit the right frequency, a high ultrasonic frequency on certain body tissues, you can actually dissolve them. So you can get rid of things like kidney stones using ultrasonic waves. And of course, while tigers and elephants and certain other animals can hear infrasonic, dogs would be a good example of animals that can hear ultrasonic. You can have a dog whistle that you don't hear, but the dog does. In fact, as you get older, your hearing range narrows more and more in this direction. I'm not sure if it narrows the other way, but an adult's range is going to be less than a teenager's range. So you can actually get cell phone apps and things like this. I'm not encouraging you to do this. You probably shouldn't. But that they'll emit some kind of a sound that younger people, I think it was like 20 and under, 21 and under, I can't remember. It wouldn't be 21 probably, that would be such a great coincidence. But under a certain age, people can hear it, and over a certain age, they can't. So if you want to drive all of the young people out of a room, then just pull out your cell phone and play that app, and you might be left alone if it irritates everyone enough. One last set of concepts we need to talk about. We talked about the speed of sound, which again was basically going to be 331.5 meters per second plus a certain amount depending on the temperature. And if you have, say, a plane, I all of a sudden just kind of forgot what a plane looks like. And it flies faster than 333.1 or sorry, 331.5 meters per second, plus whatever extra given the temperature, then that plane will be considered supersonic, traveling at a supersonic speed. And when it reaches the speed of sound, let's say it's going, 330, 331, 331.5. At 331.5, just pretending it's freezing outside, it would actually be a higher speed of sound. Then once it hits the speed of sound, it's hit Mach 1. Interesting things start to happen at Mach 1. The first thing is, imagine what happens. Okay, so my brother had an old teacher. I had him too. His name was Mr. Collier at CCS. Some of you probably know him. He's an amazing guy. But one thing my brother remembers about him was he would play football with the kids, and he would throw the ball and he would catch it himself. So he was his own quarterback and wide receiver, meaning that he could throw the ball and then run as fast as the ball was traveling and then catch it. Well, what happens if your plane is making noise because of, among other things, the friction between the plane and the air, and then of course the jet engines and all these things. The plane is making noise, and at any given moment, you have basically, let's just say that the plane is suspended in motion. It's just totally stopped. It's just floating in the air, and time is still going on, and the plane is making noises with its engines, etc. So the noise from the plane would be radiating out. Well, I should do it this way. I don't want to mess up my plane, it's so beautiful. But from, let's say there's noise in the tip of the plane. The sound waves would just be emanating out in circles, all around, nice even circles, traveling outward, propagating in every direction. But now we're going to add some velocity to that plane. If you were to throw a football and then run toward it, even if you didn't catch it, then there would be a shorter distance between you and the football than if you had simply stood still and threw it. So for example, say this guy throws a football and it goes 100 yards. But if at the same time he ran 50 yards while the ball was flying, then the relative distance between him and the ball would now be just 50 yards. So standing still, it traveled 100 yards, and then if he ran toward it, it would be 50 yards apart. So what would their relative speeds be like? If this is going 100 yards per second, and he's really fast, he's going 50 yards per second, the relative speed, if he's running, is only 50 yards. But if he's totally still and this travels 100 yards per second, then that means the relative speed is 100 yards per second. What does all this have to do with sound? Basically, if a plane is traveling, then those nice, evenly emanating sound waves coming out in perfect circles are still going to be coming out in perfect circles, but the plane is going to be moving forward faster than they can emanate out in perfect circles. So it's like running toward your football as you throw it. The relative distance between you and the football is less than if you had just simply thrown it, and same with relative speed. So this will result in something called the Doppler effect. And we've probably all experienced it in real life, especially with ambulances. Doppler effect. When an object is coming toward you, if it's going fast enough, then whatever the source of the sound waves is moving and in the same direction as the sound waves themselves, and therefore it's catching up to the sound waves. So these sound waves here might still be emanating out faster than the plane is moving, but these new ones are going to be appearing closer and closer and closer to where those originated. And so there's a bunching up in front, and so in front you have the sound waves coming in a smaller wavelength, as they're bunched up. So that's a higher frequency. And what does a higher frequency mean? Higher pitch. So the Doppler effect means that when a fast object is moving toward you and making noise, and as it approaches you, it's going to be making a higher pitch. And you've seen that with ambulances. They get closer, they whine louder and louder, or not louder and louder, higher and higher and higher, you know, when they're coming toward you. But then, if this plane passes you, what happens behind? Well, it's no longer compressed up like it was up there. It's actually going to be spread out. So then the ambulance passes you and its siren gets lower and lower and lower. So as it's coming, it's just, and then it gets, and anyway, I shouldn't be doing that in the video. So here you have bigger wavelengths, more spaced out. Something I don't do anymore is an experiment where I would drive, at the time, my Jeep toward the class while honking my horn at them, which was a great way to get out stress built up over the year. Not really. So it'll be lower frequency. Pitch is lower. All right, so that's the Doppler effect. One last thing. Let's say that this plane actually reached Mach 1. Let's say it actually got into the supersonic speed realm. What happens to the sound waves then? I'll draw another plane. Here's our supersonic one. Make it look a little faster, I suppose. So what would happen if you're like Mr. Collier and you throw that football and you are directly under it the entire time you're running so that you can catch it? Or in this case, imagine you fire, like you throw the football straight in front of you and you're just like, the relative distance between you and the football is remaining exactly the same because you're catching up to it the entire time. That's what happens when a plane hits Mach 1. Sound waves are emanating out, but because the plane is moving forward at exactly the same speed as the sound waves, they end up with this crazy Doppler effect that looks something like this. You actually make a cone of sound where all of the sound wave bunches up, and in this cone you actually, because there's enough sound occurring too, like there's the bunching and there's also just a lot of sound, a lot of power in that sound coming out of the plane in the first place. And so as the plane flies overhead, then this cone of sound, once it hits you underneath, it produces what's called a sonic boom. And sonic booms are so powerful they can damage buildings, and so planes that go supersonic tend to do so over the ocean and in places where they're not going to cause any damage. So hopefully this all made sense, especially the Doppler effect and sonic booms. I feel like that was about the hardest part. Feel free to, I don't know, message me if you need any particular concept explained better. Also, let me know what you think about this video. I think it's probably not a bad idea to play these videos at faster than normal speed if you want, because let's see, this one was 45 minutes. I can try to reduce the time, but then again, if I was doing this in class, there'd be comments and things like that. I wouldn't have gotten through all this material in 45 minutes. The next video will probably be shorter because I'll be just kind of going over examples. I don't know, we'll see. It depends. I might throw some experiments in there. So let me know what you think. Let me know if this is serving you well. Let me know about the lighting and the sound quality and the focus of the camera, and I'll see what I can do to make this work really well. Have a great night. Or day. It's night for me.